Okay, 102 students, got a little question from chapter 5, number 10. I suspect it's related a little bit to the math involved here. Let me read this one here. It says, how does the Earth's gravitational force on you differ when you are standing on the Earth compared to when you are riding in the space shuttle, which is 400 kilometers above the Earth's surface? You can take the Earth's radius to be 6,400 kilometers. So here might be a model of the Earth, and I'll put a little dot there. That's on the surface of the Earth. And above the Earth, and really very little above the Earth, I'll have to at least make a dot above it. But this extra distance is only 400 kilometers, whereas this whole diameter is 6,400 kilometers. So this isn't really drawn to scale, but you are further up. And this chapter, called the Universal Law of Gravity, is this calculation, where you multiply these three together, divide by the radius squared, and you get the amount of force on you. Okay, so it's asking you really to compare these two, and I guess there's a couple of ways we can do it. This is really kind of set up for a percentage. The first thing really says, how does it differ on you? And I suppose you could just argue here that, well, we're further up, and when R is bigger, then you get a smaller number for the force. So I guess part of the answer would be just to say it's smaller. However, that doesn't put a number with it. And if it was in the conceptual section, I guess I would have said maybe that's all they wanted. But given that it's in the exercise, I think they really want us to do a calculation. Okay, so let's say you're on the surface. I'll just put on the surface. Compared to above a surface. And so I'll say in, did they say space shuttle or the space station? Let me come back here. When you are riding in the space shuttle. All right, so I guess this is a little old question because the space shuttle doesn't launch anymore. But let me just say, all right, we're going to be in the space shuttle. All right, and I would maybe compare these two, and it would look something like this. On the surface of the Earth, I would have this G. I would have the mass of the Earth. I'll just put an E, and then the mass of myself. Why don't I just put an M? And then I would have this radius of the Earth. Depends how you want to write it. Why don't I write it as, well, first write it as 6,400 kilometers. But remember, a kilometer means 1,000 meters. So I'll put another 1,000 meters here. So this is 6,400 meters. Probably better written or talked about as 6,400,000 meters. Now, let me not forget to square it. Okay. Now, I really can't calculate a number here because I don't know, well, I guess this would be the mass of me, but everybody would be a little different. Some people have a lot of mass, some people have very little mass. So there's not a solid answer they want here. I mean, we could look up the mass of the Earth, and we know the gravitational constant is 6.67 times 10 to the negative 11. But let me just leave it that way for a moment here, because the second half of this is to do the same calculation over here. What is the force when you're in the space shuttle? So maybe over here I ought to put OS for the force on the surface of the Earth. And over here I'll put FSS for space shuttle. Okay. Now, how would I do this one? Well, it would still be the same two objects. So it would still be mass of Earth, and it would still be mass of me. And, and if you were doing the calculation, you would have a different number here than me. Okay. Now, how far away are you? And this is this whole point. They said back here that we were 400 kilometers further. Now, let me go back to chapter 1 again. This would be 400, and then a kilometer means 1,000. So this is 400,000 meters. And I probably should have done the same thing. That's what I did down here. I said this was, let me put it up here, 6,400 kilometers. And then I said, well, a kilometer is 1,000 meters. So I just put 1,000 meters in there. And that's how I got the 6,400,000. Okay, so now, being in the space shuttle, I would be this radius of the Earth, but another 400,000 up. So if we add 400,000 to our already 6,400,000, we get 6,800,000 meters. So again, without even doing a calculation, you can see that the force on the space shuttle is going to be lower because we're further away. That number in the denominator is bigger than that number. Okay. Now, the reason I said this one was set up to put a number in terms of a percentage is because if we take one equation and divide it by the other, in other words, if we take the force on the surface and divide it by this second equation, force in the space shuttle, over here we would have this G, mass of the Earth, mass of me, all divided by 6,400,000. And this one here, the force in the space shuttle, would be G, mass of Earth, mass of me, divided by 6,800,000 squared. And this is the part where if you're a little weak on your math, you may not have seen this coming, but that's why it wasn't important to really talk about the mass of the individual, because they cancel off. And for that matter, we don't even have to worry about the mass of the Earth or the universal gravitational constants. And now we can get this ratio, if you will. Now, this is a compound fraction, so on the top, I would just be left with 1 over 6,400,000 squared. And down here, if you flip and multiply, you get 6,800,000 over 1, and then squared. And so if I put this into my calculator, let's see, in the numerator, I got 6,800,000 squared. And I will divide that by 6,400,000 squared, and I get a number of about let's call it 129. And so what this is saying here is on the Earth, and maybe I should move this over here. So if you take the force that you have in the space shuttle, multiply it by 129, call that maybe about a 13% increase, you would get your force on the surface. Now, this is probably better written with this number over here. So let me move it to the other side by saying 1 divided by that last answer. And that looks about 0.886 of the force on the surface is the force on you when you're in the space shuttle, okay? And so that's comparing to the surface. So take your surface and you reduce it by a small amount. That's about all those round out to 89. So that's about 11% drop. And so you are about 11% lighter when you're in the space station. And I think this illustrated really well, Newton's universal law of gravity. But in addition to that, it illustrated how we can just compare. We don't have to really go and find things like the mass of the Earth and whatnot. And I got some other questions from students like number 18. I'll do that one next. But I think it's along the same way because it's asking you to compare Mars to the Earth. And so we'll just do kind of a comparison. We won't actually bother to work with these numbers. So the math might make it a little tricky. The author is really asking you to kind of step up your math game at this point. All right, well, I hope this one helps.